Hi guys, a while ago I picked up a whole bunch of floppy disk drives from somebody who no longer wanted them, and I thought it'd be interesting to look at how they work inside, and what the electrical interface is, and how we might set up a circuit that can read or write from the floppy disk drive. So these are the kinds of floppy disk drives that were used in the early 80s, particularly with things like the BBC microcomputer. The Commodore 64, I think, they had their own special one because they did disk drives in quite a different way to most other people. They're also very similar to the ones that were used in PCs, although they're not quite the same. The electrical interface was slightly different for those for some reason. IBM did it differently. But these are all based on what was called the Shugart bus, and that was because the Shugart company was the first people to make a mini floppy disk drive, either 5¼ inch size like these. So they kind of defined the standard that everyone else almost followed from that point on. So this is the kind of disk that was used in these drives. It's a 5¼ inch floppy disk. It's probably not as familiar maybe as the 3½ inch discs are these days, even though those are actually obsolete as well. These did come first. Prior to these they used 8-inch discs. These are called mini floppy disks because they're smaller than the 8-inch ones. And inside there's a disc of material which can be magnetized. It is a circular disc even though the outside is square. It's just an envelope that's that shape to make it easy to handle. And yeah, that's what gets the data stored on it. And the company that made these things work first was called Shugart. They developed the 5¼ inch format, the mini floppy. The 8-inch format was developed by IBM prior to that. Now, the Shugart company also developed the first standard for mini floppy drives, and the electrical interface on all of these drives is the Shugart interface. It's not quite the same as what was used for something like a Commodore 64. The Commodore 64 had a very different kind of disk drive to most other computers because it actually had a whole 6502 compatible microprocessor inside the drive itself, and it basically just had a sort of serial link between the drive and the computer. Most other systems used the Shugart bus, which is what goes down these 34-pin ribbon cables. And that means that the drive itself is only doing fairly low-level operations, and a lot more work has to be done by the host computer, either by the CPU or another microcontroller in the host computer. The IBM PC also used 5¼ inch floppy disks when it first came out, later migrated to the 3½ inch format like most things did, and they didn't use exactly the same interface as the Shugart interface. It is slightly different. They did something weird with some of the drive select lines and they swapped a few lines around. It is mostly the same but not quite the same, so if you're going to do anything like this you need to be aware of what standard your drive is actually working to, and in fact some drives have jumpers in them which let them swap between the two standards, because those two were the most common ones out there. These are all Shugart interface though, which is what the BBC Micro used, and that's kind of why I have them all, because they're all for BBC Micros. So these drives are all broadly the same kind of thing, but they have slightly different capabilities. This one over here, for example, says it's 40 track and single-sided, and gets 100K on each side of it, on one side of the disk. It only supports one side of the disk, so that's the total capacity for that one. Back in the day, you could buy single or double-sided drives and single or double-sided disks as well. And the 40 track thing depends on the quality of the disk and the precision of the drive. 80 tracks obviously stores information more densely on the disk and requires higher precision heads and also a higher quality disk. So both you had to get the right kinds of disk and drive for that kind of thing. Most of the other drives here are actually 80 track drives, and most of them are also double-sided, and the reason that's the reason this one over here says drive 0 and drive 2, and its kind of twin here says drive 1 and drive 3, and that's because on the BBC Micro, which these were intended for, the two sides of the disk were actually given different drive letters. It was a bit weird. Anyway, the disk itself, as I said, contains a circular recording medium, and there's this hole in the middle with a protective kind of plastic reinforcer on it, is for the drive to grab hold of and spin the disk. Obviously it doesn't spin the envelope, it only spins the disk inside the envelope, and this little window allows the read-write head to access the surface of the disk. And the head itself has to move backwards and forwards across the range of this window to access different tracks on the disk. The tracks are numbered from the outside to the inside conventionally, so track 0 is at the outside. And these are 40 or 80 track, depending on how you count, and either way they just increase towards the middle, so the inside is either track 39 or track 79. In fact, the discs tend to have a little bit more space on it that you can use if you want to, but conventionally that wasn't used. There's also a little notch here which is used to indicate whether the disc is write protected. So if that notch is not present, or if it's covered up with a sticker, then the drive will signal to the computer that the disc is write protected, and the computer should then not attempt to write to the disc. It doesn't actually prevent the drive from writing to the disc if you tell it to, but we'll come to that a bit later. That was all a software thing really. And there's also this little hole here, which if you turn the disc around, at some point on the surface on the disc itself, there's a corresponding hole in the disc, and this is used to identify a particular part of the disc. There's only one hole on the entire revolution of the disc, so as the disc spins in the drive shines a light through this hole, and it can detect once per cycle when the disc has done a full rotation. That's actually less useful than it might seem. Most operations to the disc don't really pay attention to that, but certain things like formatting can use that hole to kind of synchronize the start of each track at the right place. For most sort of sector seek operations, it actually uses data written to the disk itself to work out which sector is which, so it doesn't really need to know where the start of the track was. There's also two notches at the top here. I have no idea what those are for. But yeah, that's about it for these floppy disks. Usually they have a label on them, this one doesn't for some reason. But yeah, let's have a look at the drive. So this drive looked like it was in pretty good condition. It's quite clean. It was actually inside the case, which is why it was so clean. Some of these other ones that are outside their cases are quite dirty, and I don't really want to use those without cleaning them pretty thoroughly first. But this one's in pretty good condition, and you can see one side and the other there. And that's what they look like from the front, which is fairly typical. This switch actually allows this drive to switch between 40 and 80 track mode, which is quite handy. And there's this kind of door mechanism which holds the disc in. And there's a light on the front as well that tells you when the drive is in operation. So fundamentally, what the drive has to do is accept a disc and grab hold of that central part of the disc and spin the disc round, and they spin at 300 revolutions per minute on these drives. That's 5 times per second. It probably doesn't sound very fast, and it's actually slower than I expected it to be, but yeah, that's how fast they went. And the whole point is to move the magnetic recording medium past the drive heads at a fairly constant speed, and then changes in magnetism on the disc cause changes in current through the recording head, or maybe it's potential, I'm not sure which. These changes are then amplified through differential amplifiers because it's a very, very small effect. It has to be small because it doesn't want to actually erase the magnetic data in the process of reading it. So that current difference or voltage difference is magnified through the amplifiers and then essentially gets spat out by the drive for the host computer to interpret. In order to read both sides of the disc, there are 2 recording heads, and they are attached here. I'm not sure how well that will show up on camera. Let me see if I can get a good shot of that. You can see the white thing underneath there is the bottom recording head, or read-write head. I might be able to get a view from the side here as well. You might be able to see the top one as well there, I'm not sure. But this top one is actually mounted on an arm that moves here, and in fact when you close the locking mechanism at the front of the drive that holds the disc in, it also moves the head down onto the disc surface and kind of, I think they actually touch the disc surface, I'm not totally sure, they might just be slightly apart above it, but yeah, they move down to get into proximity with the disc surface, and they sort of hold the disc between the 2 heads so that they get good signals on both heads. It also clamped the motor here as well, so this is the top spindle of the motor that spins the disc, and closing the mechanism also clamps that onto the disc as well. There's a little white thing here which I believe is slightly sprung, and it might be intended to spit the disk out a little bit when you open the drive. It doesn't actually work on this drive for some reason, but sometimes they do that. So when you open the drive, it pops out a little bit to make it more easy to take out. Let's have a look at the back. So on the back here we have the main motor that spins the disk. I'm not quite sure what kind of motor this is. It's obviously it's a funny shape here, but they're always done that way as far as I've seen on the other ones as well. I guess it's to fit them inside the shape of the case here. And that motor has an associated circuit board here, which I guess has some form of speed controller on it, because it is required to spin at pretty precisely 300 revolutions per minute. If it deviates much from that, then the software won't be able to actually read the disk anymore, and it also breaks compatibility with other drives. And over here we have another motor. This is a stepper motor, and this is used for positioning the drive heads, and I'll show you how that works in a second from the other side of the drive. This is the main circuit board. As you can see, there are a few ICs on here. It's not completely trivial what the drive is doing here. This is the power connector, and this is the data connector here. Like I said, there's a very standard kind of arrangement for these pins. And here we have some dip switches that are used to configure the drive. It's actually currently set to be drive 0, and the interface allows up to 4 drives to be connected simultaneously. And they show all the pins, but 4 of the pins are selection pins, and this just chooses which of the selection pins this particular drive is going to be listening for as an enable pin. It's very much like the way a lot of the ICs that we use in our computers work. Back on the flip side then, we have the head assembly, as I said, and the stepper motor basically has this metal ring round it, so when the motor moves, it shifts the head assembly as well, and I can actually push that by hand. I don't think this does any harm, and you can see that the motor rotates as I move that head assembly backwards and forwards. And it uses that to position the head at the track it wants to read from. Other things going on here is a little LED here, which is there to shine through the index hole that I showed you earlier, that little hole near the centre of the disc. And on the flip side there's some kind of light sensor or infrared sensor, it's probably infrared, which detects when the hole actually passes. There's the LED for the front here, which is used to show the activity of the disc. There's another LED here which shines through that little notch in the side of the disc to determine whether the disc is write protected or not. And the switch on the front, as I said, is actually connected to this wire, which kind of it's just been soldered onto the board here. That's probably retrofitted, it probably wasn't part of the original drive here. A lot of drives did have this 40 or 80 track option, which you could enable, but they may not have had a switch for it. And the way that switch works actually is that every time the computer asks to step from one track to the next track, it actually just steps twice in 40 track mode. So it's still kind of working as an 80 track drive, but every time it wants to step one track, it actually steps 2 instead. One other thing which I didn't mention about the way the heads are positioned is there's a mechanism for detecting when it's reached track 0, and that's actually this black thing here. Not sure how well that'll show up on the camera. That is another light sensor with an LED one side and a sensor the other, and as the heads move towards the outside of the disc, this black fin here interrupts the flow of light, and when that happens the drive knows that the head has reached the outermost extent, and that's called track 0. And there's a special signal on the interface that actually tells the host computer when it's on track 0, and that's to provide the host computer with a reliable reference point for which track it's actually on. So I can show that with a disk inside, just so you can see how this all fits together. The disk obviously fills that much of the drive, and yeah, it just slides in like that. You can see that the little window thing goes between the heads, and then when I close this down it clamps onto the disc and moves the head down to touch the disc surface, and that would be ready to go. So let's see if we can actually get this powered on then. I took this drive out of the box over here, and it has a power supply in the box as well, which takes a standard kind of mains power here. A lot of these drives actually plug straight into the BBC Micro. They've got the special plug on them for being powered by the computer itself. But for this experiment I wanted to pick one with a mains power supply so I don't have to actually rewire them. So that's now turned on, and we don't really expect anything to happen because it's got no data interface plugged into it. Now the way the data interface works is all the signals are active low, but the drive itself has pull-up resistors on them, so it assumes everything's high by default, which mostly equates to off. You will see, I don't know if you can hear that, the motor's actually spinning now that I've put the disc in there. I'm not entirely sure why it does that. I can show you this way around. You'll see the motor start spinning as soon as I start inserting the disc. No idea why that is. And it stops after I close the door. Anyway, we're not going to get much out of that with just putting the disc in it, so why don't we try plugging something into the back? So before we plug anything in, let's have a quick look at what the interface is on these things. Like I said, there's a 34-pin ribbon cable, and I've actually made a quick breakout for it here using DuPont cables. But I wrote a little legend here to explain what each of the pins is for. So these are all of the signals which are present on the 34-pin ribbon cable. I left out every other wire because every other wire on the ribbon cable is ground. So we have 17 wires left here, and actually some of these are not used either, for my purposes anyway. So let's go through them quickly. So the first one here is disk change detection. I don't think this was a standard feature on all drives, but it was a way for the drives to tell the computer that the disk has been changed. This one is in use. I think that was a signal from the computer to the drive, but I'm not sure. Again, I don't know much about this one, but it may have been used to tell the drive that actually it was meant to be doing stuff at the moment. I don't know, it's a bit confusing. I'm going to skip this one for a moment. The next one here is the index line, and this is a signal from the drive to the computer, which gets pulled low by the drive each time the index hole passes the sensor. So once per cycle of the disk, this gets pulled low. All of these signals, by the way, are active low with pull-ups on the receiving end. So the ones that are from the computer to the drive has pull-ups. The ones that are from the drive to the computer has to have pull-ups. So going back to this one and the next three are all drive select lines, and the computer has to pull one of these low to make the corresponding drive be active and let the corresponding drive actually use the rest of these inputs and outputs. Drive select 0 is the only one I really care about, because this drive is configured as 0 and I'm not going to plug two in at once. After the drive selects, we have load, which I believe is meant to be a signal to cause the head to descend onto the disk so that it's ready for use. But I mean, I've heard that in practice what this actually does is turn the motor on. I think the motor might be connected to this signal rather than the head positioning being driven by it, because the head position here is controlled by the lever, as we saw earlier on. This next one is direction selection, and in conjunction with the one after it, which is step, this controls the position of the read-write head along the tracks. So whenever step goes from high to low, the head will step one track in the direction specified by the direction pin. Not totally sure which way around that is, but one way or the other, that lets you control whether you want to step in or out on the disk. Next we have write data. This is data from the computer to the disk drive, which should be written to the disk. And we have write enable, which controls whether the disk should actually be writing data at the moment or not, because most of the time the disk will be in read mode. The next signal is from the disk to the computer. It's called T0, track 0, and this one goes low when the head is at track 0 using that light sensor I showed you earlier on. So that should just stay low all the time whenever the head is on track 0. So for most purposes, in terms of positioning the head, the computer has to kind of keep track of which track the head is on at the moment, and step however many times it wants to change tracks. The only time it can be really sure exactly which track the head is on is when it's on track 0. So usually the first thing a computer would do is just step the head all the way to the outside of the disk until that T0 signal goes low. Also, any time that the computer gets confused and loses track of which track the head is on, again it should step to the outside and find track 0. The next signal here is write protect. This is a signal from the drive to the computer which tells the computer whether the disk is meant to be write protected. Completely advisory, the drive will still write, I think, even if this signal is low. So it's up to the computer software to actually pay attention to that and not overwrite disks that are meant to be read-only. And the next signal here is read data, and this contains the data stream from the drive to the computer from the read head. When it's not in write mode, this will continually show the data that the head is currently reading. The next one is side select. So for these double-sided drives that have 2 heads on them, this just controls which head is active at the moment, so which one is reading or writing. And the final pin here is a ready pin, which I'm not entirely sure what it's for. So I've made a kind of a breakout here using DuPont wires for the pins that I actually care about, and I've used different colours for different things, and I put a little note on the paper here about which colour is for which signal. So let's go through just quickly once more time the ones which I'm actually going to be using here. First of all, we have orange for the index pin, so I'm going to be able to tell when the index hole passes the sensor. I have yellow for drive select 0, and I'm pretty much going to just tie that to ground so that the drive 0 is always selected. I have white for load, which I think is the motor control, as I said before. Green and purple are for direction and step, so those are going to control the head position. Blue is the data to be written to the disk. Green is the write enable line. Yellow is track 0 indication, and I'll probably play with that a bit with some LEDs to see if I can tell when the head's on track 0. Orange is write protect, which I don't really care much about, but I put it in anyway. And red will be read data, so this will be a data stream from the disk. And if I get time, I might actually connect that up to an oscilloscope and see if we can see what that data is. The rest of the signals I'm not going to bother with, because they're all active low with pull-ups on the reading end, on the receiving end. If I don't connect any of these signals, they'll just be inactive. So things like side select, even if it's not connected, it's still going to have a consistent value because I'm not pulling it low. And similarly for the drive selects for drives 1, 2, and 3, they're not going to cause any problems because I'm just not sending anything, and the drive won't care about that. So I've changed the camera angle to get a bit better view here. Let's just move that so that it's still maybe visible. I don't know whether that's visible. I'm going to connect the ground from the drive to the ground from the power supply I've connected to this. It's a 5-volt DC power supply as usual powering this board. Just going to connect that on so that they've got a common ground. And now I should be able to connect the drive select, that's yellow. If I connect this one low, then it should select the drive. And yeah, the light's coming on the drive when I do that. So that's good. What else can we do? We can connect track 0 to one of these LEDs. So track 0 was the yellow wire from this side. So let's grab that one. Try and dodge all these. There. None of these really matter if I short them because they're all open collector, so that's fine. So I'm going to connect that to this. Oops. I messed up the resistor there. So I'm going to connect that to this LED, and that is indeed lighting up. So the head is currently on track 0. I'm not going to push that with my hand again because I only did that because it wasn't powered on at the time. I don't think I should fight the stepper motor when it's actually powered on. What else is interesting? I could put a disc in, actually. Let's put a disc in. and this is the index signal, which will toggle once per revolution of the disk. So I'm going to connect that to the other LED and see where we can see that. So it's not lighting up right now, so I guess the index hole isn't in position there at the moment. But what we should be able to do now is turn the motor on. Which one was that? That was the load line, which was white, so that would be this one. If I put this onto ground, the motor should come on. And it does. Oh yeah, and you can see the LED lighting here. So this is the index indication. So it should be 5 times per second, from what I read, 300 RPM. I don't know, it's probably about right. Anyway, so the drive is flipping that one low briefly 5 times per second as the index hole passes the little LED thing here. Let's turn the motor off again, because I feel a bit sorry for it. Just stick that somewhere for safekeeping. I can't get it in. There we go. So what can we do next? We're currently indicating that we're on track 0, so let's see if we can get the head to step. So you should be able to see the head move over here when I do this. So purple is the step signal for the heads. So let's just try bringing that to ground. See what happens. Okay, nothing happening there. It may be because the direction is in the wrong direction. So if I take the grey wire and connect that to ground, that will flip the direction to be the other way. So I guess when the grey wire is not pulled to ground, then the stepping is towards the outer track, but it's already at track 0, so nothing happened. I'm hoping that's what happened there anyway. So if I take purple to ground now, hopefully we will step away from track 0. Oh, there it goes. It looked like it did that when I pulled it out, so I guess it's on the rising edge of this signal. It moved one track outwards. I don't know if you can hear it as well when it does it. And if you look over there, you'll see the head's actually moving. Oops. Yeah, it wants some debouncing really. I'm sort of making a bad connection here. And that moved towards the centre of the disc. Oh, it's making a different sound now. I guess that's as far as it goes. So it doesn't have a sensor that tells it when it's on the innermost track, only on the outermost one. So I guess you shouldn't go too far inside. If I take the grey wire out again now, then we should be able to step outwards. And eventually we'll get back to track 0 again and the LED should come back on. There we are. And the drive's ignoring any further pulses I send down this link. So that's nice, that's handy. I wonder whether we should try and actually read some data from it now then, because most of the remaining signals are just for the data reading and writing, aren't they? I could play with the write protect thing, but that's a bit boring. Let's not bother with that. I'm going to plug in the oscilloscope and see whether we can read some data. So they're the scopes on there now. What I think I should probably do is... I already put some little stubs in here to help me with this. What I'm going to do is connect the ground of the scope to the ground, to the common ground. And I'm not sure what that's triggering on actually. I'm going to connect the yellow probe to the index hole, I think. Let's do that. So, ground's really annoying. Do it from that side instead. Oops, that's come out. There we go. So I'm going to connect. I've got a pull-up resistor here because, as I said, all of the signals from the drive to the computer and from the computer to the drive are open collector, so I have to pull it up myself here. So that's what I've done. That's quite a big pull-up resistor. It's probably meant to be less than that. And I think it's meant to be 150 ohms, but I've got like 5k in there. I think it's probably all right. So let's just check the settings on here. We've got 5 volts. Yeah, 5 volts is good. So I'm hoping that we'll see a regular signal on there when we spin the disc. So let's give it a go. Let's just try that. So yellow was the drive select, so I'm going to turn the drive select back on again now. Here we go, the lights come on. And which one was spinning the disc? Was it the white one? Yes, the white one. So I'm going to connect the white one to ground as well. The disc will spin, and nothing. Oh, I didn't connect the index wire, so the index wire was orange, I think. So connect the index wire to what the scope is reading there. There we go. Got a nice little notch there. Let's change the horizontal so that we can see several of those. Oops, that's a bit too far. There we go. So that's a horizontal time base of 50 milliseconds per division. So that's 1, 2, 3, 4 times 50 milliseconds. That's 200 milliseconds between pulses, which is exactly right for 5 revolutions per second. That's actually pretty precise. I suppose I shouldn't be surprised. It's quite important that this is accurate. So we're getting a little notch there every 200 milliseconds. So that's great, and I'm triggering on that notch. So everything else I do will be relative to that. So I guess the next thing to do really is to actually use the read data signal. So read data I've got in red here, and I have another pull-up resistor here that I can use for this. So let's plug the read data into that pull-up resistor. Again, I'm pretty sure even for things like the data lines, I'm pretty sure that the drive is only going to be pulling them down, and it's up to me to pull them up. So let me get the next probe. And I'm going to wire that to ground again, like the other one. Oh, it didn't like that very much. Huh. There's a bit of a glitch there. And I'll connect it to the read data line. Oh, I need to turn on the actual scope trace. Okay, so there's channel 2 on there. That's a bit of a mess. I thought that would be more consistent than that. Because in theory, every time this disk goes round, it's going to reread the same data stream, so it shouldn't be random. Let's sort of zoom in on the start of the trace here and see what we've got. Because there's quite a lot of long periods of high here as well. It may be that the signal's just too high frequency for the scope at that granularity. That's better. There we go. That'll be it. So because I zoomed out quite a long way on the scope, it wasn't doing the sample rate wasn't high enough to capture the signal. So my understanding is that these signals are approximately 4 megahertz. So we need a pretty high sample rate to really capture them. Sorry, not 4 megahertz. The opposite. 250 kilohertz. Anyway, so let's get the falling edge of the index signal here and see what we can see there. Yeah, now we're getting a lot more consistency. Look, so it's got some fairly frequent drops at first, and then it's got these quite long regions. We can probably get a closer look at that. Just move that across again. So my index pulse starts over here. Let's get a single capture of that. And now we can look in a bit more detail. So what time base are we at now? That's 1 microsecond per division. So each of these little pulses down here is 1 microsecond long, and then it seems to stay high for 3 microseconds and go down for 1. So like I said, I was expecting this to be around 250 kilohertz, and that is what this is. This is like a 4 microsecond period between these things. my understanding is that is the frequency that you're supposed to record data at on these disks, although it's probably somewhat up to you how quick you actually go. If you try and do it too quickly, you're going to start running into problems with the quality of the disk surface and whether it's able to have enough magnetic transitions in a short sort of physical distance. And that's going to get worse towards the centre of the disk as well, because the middle of the disk is spinning more slowly than the outside is in terms of linear speed. So if you were going to get errors due to the magnetic flux not being dense enough, it would be at the centre rather than the edge. So that's nice. I did see earlier when I zoomed out, we're still looking at the single shot capture I did a moment ago, and it's not actually live at the moment. In fact, we could turn off the disk, maybe. There we go. There's no point spinning that with the heads on it if we're not actually reading stuff from it. Yeah, so I noticed that this here is the 250 kilohertz signal with 4 microsecond period. This one here is slightly longer, so let's have a closer look at that. And on the left there you've got one of the 4 microsecond period ones. This one here is 1, 2, 3, 4, 5, 6, 7, 8 microseconds. Yeah, so that's the same rate. It's almost like it just sort of missed a pulse here. And that's the main way that this system works, from what I've read. It's a little bit confusing. I was reading about FM encoding, which is not the same as FM radio encoding. It's a mechanism to ensure that there are frequent enough transitions in the flux on the disk. You don't want to have long periods of high or long periods of low, because that's not compatible with the kind of recording medium. It requires changes at a fairly high rate, but not higher than a certain amount, because, as I said, the flux density on the disk is not high enough for more than a certain frequency. So what you have to do is make sure that the transitions happen at least a certain rate, but no more than a certain other rate. My understanding of how this works is quite limited though, so I'm going to have to do some more research on that, and I might have to leave that for another video to look into that in a lot more detail. Anyway, that's kind of interesting, I think, what we're seeing there. Let's turn the disk back on. Oops. Wrong wire. There we go. Let's have that running again. So it's fairly consistently reading some number of shorts there, and then 1, 2, 3, 4, I can't count them. I guess there's about 6 long ones there. It looks like there's an intermediate one here as well. That one there looks slightly longer to me. So one thing that might be happening here, because this is the very start of the disk, this area probably doesn't actually get written very often. It was probably written once during formatting. And what might have happened was that the formatter would have started writing the track at the start of the when it saw the index pulse, and then it would have written the track, and then when the next index pulse comes, it has to stop writing, and it might have a bit of a delay before it stops writing. So that maybe that's what's going on here. I'll zoom out enough that it works, and I can see those. Yeah, I can see those long pulses there. I just want to move to the right until something else interesting happens. Yeah, there we go. There's some more long pulses here. It's a bit hard to see. They're moving around a bit, because I think this is because the speed of the disk isn't 100% constant. So the further you go away from that index pulse, in terms of the relative time on the oscilloscope, the less stable it's going to be. So my understanding with FM encoding then is that when it's doing the fast pulses like this, that's 1s, and when it's doing the slow pulses, that's 0s. So the general principle, I believe, is that you output 1 notch per clock pulse, and you do these clock pulses at 125 kilohertz. So that would be an 8 millisecond, so 8 microsecond period, and that's essentially these are the clock pulses. And then in this bit, what you're seeing is in between the clock pulses, there's also a data pulse, and that indicates that these are 1 bits. Whereas over here, there's no pulse between the clock pulses. You can't see the data pulse, and that indicates a 0. So I mean, that's the general principle behind FM encoding, as far as I know. So yeah, it sort of makes sense, I guess. Just going to keep moving to the right, and then hopefully we'll see something more interesting than lots of 1s and lots of 0s. Yeah, there we go. Now that's an interesting one. So that looks like the start of some interesting data there. Let's zoom in a little bit more on that and see what that is. So we had some 0s, and then we had some 1s, and then some more 0s here. Oh wait, no. Oh, that is interesting. That's not a valid FM signal. So these are clock pulses. Sorry, no, wait, let me go back further. These are clock pulses. So this is a clock pulse followed by a 0, then a clock pulse followed by a 1, then a clock pulse followed by a 1, but then we have a missing clock pulse. I think this is... I need to do more research on this, but I think this is a special tag that's used in this particular disk format to indicate some metadata. That would make a lot of sense, actually. So this would allow the disk controller to spot, for example, this might be the start of a sector or something like that. So this would allow the disk controller to look at this data stream and spot the start of a sector without there being any risk of the same byte sequence appearing in a valid data section of the disk. So I think what it's doing here is it's missing out some clock pulses in a way that it would never do when it's writing a sort of user data section to the disk here. Let's see what it actually did there. I'll have to look this up. So let's assume that these were 0 bytes. So this is probably the start of a new byte here. So that would be 1, 1, 1, 1, 1. Is it just 1s all the way along there? Let's just check that again. Clock pulse 1, clock pulse 1, missing clock pulse 1, missing clock pulse 1, missing clock pulse 1, clock pulse 1, clock pulse 1, clock pulse 0. Okay, so the data byte here, assuming I'm right, the data byte here would be FE, because its bottom bit was not set, and then the clock byte would be 1, 1, 0, 0, 0, 1, 1, 1. 1, 1, 0, 0, 0, 1, 1, 1. So that would be C7. I'm going to write that down. So that was what? F, E mixed with C7. I have to look that up and see whether that means anything. Yeah. This is kind of interesting looking at the disk like this. After that, yeah, I guess we get some 0s and 1s and things like that. This looks like it looks like a steady stream of clock pulses again now. Yeah, so I'm pretty sure that's what will be going on there. The missing clock pulses will be a special signal that's a special kind of data. Most likely the start of a sector, I think, something like that. Anyway, very interesting. I'm going to have to look at this in more detail through more powerful means than an oscilloscope. I'm in two minds about this. So what I could do, one thing I could do would be to wire this up to something like a Teensy, which is like a super fast version of an Arduino, and that would allow me to sample this at a high frequency and maybe do some software analysis of it. And another option is to just go ahead and try and make an electronic circuit that can read this, which would be interesting too. Actually, before I wind this up, I did want to actually try writing some data as well, so let's give that a go. Yeah. So I believe in order to write data, we need to bring the green wire, which is write enable, low, and then the drive should immediately switch into write mode. With the disk already spinning, we would want to turn that on. The idea is that you turn that on when you reach a point on the disk where you actually want to write data. So you'd normally be looking at the read data stream and watching out for something like a sector marking that says the sector that you actually want to write data for, and then you would bring the write enable low and start sending data out of write data. And it would overwrite that bit of the disk until you brought the write enable high again. So normally you'd bring that low fairly briefly during the course of the revolution of the disk. But I could just take it low all the time, and that will then just write loads of data. What I do need to do is generate a signal for the blue wire, which is the write data line here, and then we can check whether that actually gets written onto the disk. So let's just turn this back on a moment. I'm going to zoom in on the start of the track where the index hole is, and again we can see this same pattern we saw before, where we have the 250 kilohertz signal first and then a short period of 125 kilohertz, which, as I said before, these are going to be clock pulses. These will be ones and these will be zeros in the FM encoding. So I'm going to leave that like that, I guess. And if I now take, well, let's try taking write enable low without actually providing any data and see what happens. I would expect it to just corrupt this. I don't know what the result's going to look like. So that's the green wire going low now. You can see that the reading stopped when I did that, and that's come off again now. So that's the new data that we're getting back from the read head. And as you can see, that's really erratic. There's no longer any stability to that. So I think what's happened here is because we didn't actually provide a signal that was at the right frequency, the magnetic transition, there are no magnetic transitions on the disk, and the amplifier logic in the drive is just going crazy and just amplifying noise there. I'm guessing anyway. I think that's probably what's going on. I'm not an expert. So what I want to do is try and actually provide a signal for it. I wonder, I think I can use, I have this wave gen thing in the oscilloscope. Let's see if we can use that. So we have square wave, frequency, so frequency we can go for 250 kilohertz, I guess. Oh, this is so hard to use. There we go. So we're going to generate 250 kilohertz. 5 volts, fine. Offset sounds good. Duty cycle 50. So to generate, normally a 250 kilohertz signal would be 2 milliseconds low, so 2 microseconds low and 2 microseconds high. I want it 1 microsecond low and 3 microseconds high. So I probably want a duty cycle of 75, I should think. So let's do that. So that's now active as indicated there. Where's the thing? So I need to get the ground again. And which wire was it? Blue. Blue is the right data wire. So I'm just going to... Oh, hang on, no. That's not going to work like that. I need a pull up. Actually, no, that should be fine. It's a bit weird because the scope is going to be driving this both high and low. I ought to be doing an open collector, but I'll just do it anyway. So that's blue. Blue now has that signal going into it, 250 kilohertz with 75% duty cycle. So now if I take green low, once again we see the read data stops coming in on the oscilloscope up there, and we go high again. Yeah, that's better. Look at that. Perfect. So we have written, jumps around a bit, doesn't it? I think there's a delay between the index hole. I think the index hole signal isn't consistent actually. But if I capture that, what we should have is, as we said, a signal of, yeah. So again, I've got the time base set to 1 microsecond, so we're low for 1 microsecond, high for 3. So that worked, that wrote our data to the disk. I wonder, I could actually, yeah, I could, how can I write something else? I could do 125 kilohertz instead. Let's try that. So that's frequency, oh god, wrong button. These interfaces on scopes are really annoying. So I'm going to go for 125 kilohertz, and I want the duty cycle to be a bit different now. I can't divide this. 25 divided by 2 is 12. So you're about 88 then. So that's now generating 88 instead. Let's write that. And zoom out a bit. Actually no. I could just do single capture. Yeah, so now that's 1 microsecond low and 7 microseconds high as expected. So that's great, we're able to write data to the disk. It's in a funny format, it's not the official format or anything like that, but it is working. So yeah, that's nice to see. So I'm going to have to think now about what we do next, because I can see a couple of options here. One of them is that I could hook up like a Teensy or an Arduino or something. I mean, the Teensy is like a faster version of the Arduino, so I could hook up a Teensy to sample an entire track of the disk and do the FM decoding in software, and just have a look at that to see if I can make sure I understand the format that's being used on a standard floppy disk format here. I believe it's the IBM standard format. I mean, so the other thing is I don't have to actually use that format. It may be that for my purposes it's easier to just make up my own format, and I could make up something which I can more easily make an electronic circuit for. I'm going to have to make sure that I do keep up the frequency of the data. As I said, it has to be in that range of 125 kilohertz or 250 kilohertz. But there are other ways of doing that. I can use FM encoding, for example. So the thing I'm worried about is these missing clock pulses in the, I think it was in the sector header there. And the reason I'm worried about that is it's going to make it difficult to synchronize the read circuit on the clock pulse if the clock pulse isn't always there. So it may be better for my purposes, just for testing things, to have the clock pulse always present. I can still use FM encoding for the data, and I can just use special sequences in the data to kind of mark up where my data begins. Anyway, there are tons of options there. I don't have to do something practical here. I'm not really intending to actually hook this up to like the 6502 or anything like that. I'm mostly interested in playing around with it for the sake of it and investigating whether I can make a circuit that uses it. Back in the day, in something like the BBC Micro, they didn't really have a circuit doing all this stuff. It was done by a thing called the 8271 floppy disk controller, and the 8271 is actually quite a powerful microprocessor whose dedicated function is reading disks and interfacing with them, and it actually deals with all of the details of the standard track format itself, so you don't have to, either in your software really or in your hardware. But I don't really want to use one of those. It's a bit like with the video circuits, where I didn't really want to use anything like a 6845 CRT controller, because I find it more interesting to just wing it and do it myself, even if it doesn't always work. Anyway, I'm going to call it there for today. Hope that was interesting. It's a bit different to some of the stuff I've done. Please do let me know what you thought, and if you've done anything like this yourself, I'd be really interested to hear about it, as always.